Hey guys, how's it going? Today we're going over deviations from that ideal gas law. In other words, what happens when a gas doesn't act like we want it to. There's a lot of reasons why in the real world things don't happen ideally, things that we don't really take into account. That's true for a lot of things in science. We try to model something, we try to say, this acts like this, this acts a certain way, but in reality, we don't really take into account all the little things that can affect things. For example, if I say I need to travel from my house to work, it's going to take 15 minutes. I'm not taking into account the things like traffic. I'm not taking into account things like stoplights. If I hit every single stoplight on the way to work, it may take me 20 minutes. But I still say it takes me 15 minutes to go to work. I'm not taking into account certain things. Same thing with the ideal gas law. We don't take into account certain things. And in extreme situations, those little things that we didn't take into account start adding up. So we need to start thinking about what those little things could be. That way, in those extreme situations, we can handle it. We know what's going to happen. So, as far as what we are actually doing, all that we are wanting to know here is being able to describe and explain what is happening. There's not going to be a whole lot of hard calculations that you need to do. It's going to be just more of a, under this extreme situation, how does it deviate from the ideal gas? Why does it deviate from an ideal gas law? So this is more of the hows and whys and less of the calculate the thing. I'll get into a little bit about the calculations, just a little bit, but not actually like formally go through a process. Let's talk about what we actually are seeing here. So this is a graph. On one hand, or on one axis, we have PV equals nRT. PV divided by nRT. So if PV equals nRT, if we divide 1 over 1, that's going to be 1. So if we put 2 over 2, it's going to be 2. It doesn't matter what you have for pressure, volume, number of moles, gas constant, or the temperature. If you put PV over nRT, it should always equal 1. So that's why we have this little dotted line here that says this is the ideal gas. Now, if we actually look at the gases, this is what PV over nRT actually looks like. And this is at extremely high pressures. So this is whenever we start getting, remember, the pressure that we are used to is 1 atmosphere. And so when we get up to 200, 400, 600, 1,000 atmospheres, then the gases start behaving differently. There's something there that we didn't take into account before, whenever it was just 1 atmosphere. A very small thing that was happening, but it didn't change much. Now that we're at these higher atmospheres, that small thing, that stoplight that we kind of forgot about and didn't think about, is becoming a problem. Okay, and the same thing is true at very low pressures. It still deviates slightly. So why is it that these guys are deviating? Well, one thing is the volume. So when we talk about volume, if I have a 1 liter container here and it has a whole bunch of little molecules flying around, I say that we have 1 liter of empty space, 1 liter of stuff, of things. Now, the thing is that those gas particles actually do take up space. They do have a certain volume in there. And if I wanted to really be accurate, I would have to say that this space is 1 liter minus the volume that's taken up by all of the gas molecules. Now, most of the time, that volume that we subtract is going to be very, very small. So it's going to be like 1 liter minus 0.000000000000000000000000000000000000000000001 liters, which is essentially 1 liter. We can ignore that. But if we have very high pressure or very low volumes, then that is going to change. If we have 1 liter minus 0.9 liters, all of a sudden now that becomes something that we need to think about. So, low volumes, high pressure, we have to start thinking about the volume of the gas particles that subtract from the volume of our container. Okay. So that's one thing that we can think of. Another thing we can think of is those intermolecular forces. So everything is going to have some form of intermolecular force. Everything's going to be attracted to each other in some way. Even something that is very, very unreactive, like this neon noble gas, is still going to have those van der Waals forces, those London dispersion forces, because the electrons are going to randomly be on one side, right here, and which makes a slight negative charge, which is going to push these electrons over, making a positive charge, and that positive negative charge is going to have a slight attraction. So there's still going to be, even in something like a neon, that noble gas, that there's still going to be some stickiness, some force that's going to keep these together. It's going to be very weak, very, very weak, but it's still there. So think about this. If you had an ideal gas with no attractive force between anything, then a particle slamming against the wall would go through, slam against the wall at a little bit higher pressure. But now that these guys, if we include those intermolecular forces, these guys now all attract each other. So instead of, a ball smacking against this, now I have a little bit of an attractive force slowing that guy down, meaning that the frequency and force that that particle is hitting against the container is a little bit less, which changes things. So if you have more intermolecular forces, it's going to slow down this particle. It's going to hold it back a little bit more, which means it doesn't hit the container very hard, which means that the pressure is going to be less. So if we had two particles, let's say we had, let's write these out. So let's say we had neon, and these particles were all neon. Like I said, that the only thing really you have here is those van der Waals forces, those London dispersion forces. The London dispersion, van der Waals forces, same thing. So if you had neon, which side would it look more like? Would these forces be present? Well, they are present, but they're not very strong. So it's going to behave more like an ideal gas than something like H2O. H2O has lots of those hydrogen bonds that are very, very strong. If you don't remember that, go back to my intermolecular forces video and we kind of run through the different intermolecular forces. So hydrogen bonds here are going to be very strong, and since they are very strong, that means that these forces are going to be a lot stronger, which means it's going to drag this particle down, and so it's not going to hit nearly as hard against the container as compared to neon. So which one of these guys is going to act more like an ideal gas under high pressure? It's going to be neon, because it has less of those intermolecular forces, less drag on the particles slamming against the side of the container. You could also say the same thing. Which one of these is going to be more like an ideal gas, neon or H2O, in terms of volume? You can think about it that way. Like neon is just one atom by itself, right? H2O, though, is going to be a molecule. So if anything, it's going to be larger in volume than the neon. So if I asked you in terms of volume, which one is going to be more of an ideal gas at high pressure, low volume, you could still say neon. So that is the kind of the hows and whys. Let's get into a little bit of these calculations. Everyone remembers the old PV equals nRT. So PV equals nRT. So what were the two things that I said kind of changes under extreme situations? I said that the volume we have to think about. So we have to do something about this volume term. We have to change up this volume term somehow. And we also have to talk about the pressure. The pressure, because those intermolecular forces are going to drag down on the slamming up against the side of the wall. Uh, we have to think about pressure, because pressure is going to lower, because the more intermolecular force something has, the more it's going to pull down on the slamming against the side of the walls. So we have that. Now we can go through and kind of we can go through and experimentally put numbers to these things. I'm not going to go through and ask you to memorize this real gas law. If I, assume that they're going to give it to you, if you don't. And also with this particular test coming up this year, you can Google it. So in terms of that, you can just Google. You'll have pressure, you'll have volume, you'll have number of moles, temperature, just like before. The only difference is that you're going to include this A constant. This A constant is going to change your pressure somehow. So you can go through and see, how does A change? Well, like I said before, like I said before, neon here is not going to have very strong intermolecular forces. It's not going to change the pressure very much compared to something like water. Water is going to have those hydrogen bonds, in which that means it's going to change it a bit more. And you can see that's true. Neon, this is not going to change the pressure. If I had a pressure of 2 times 0.2 is not going to be a huge change compared to 2 times 5.46. So, so this makes sense. This is one way you can kind of tell what each gas, or I should say, this is one way of telling. This is one way of telling you how each of these gases are going to change your pressure. Is it going to change a little bit, like helium, or is it going to change a lot, like this chlorine gas? Okay. Another thing you can think about is B. B is going to be how the volume changes. So you can use this to help us determine, how does the volume of these particular things change. And this kind of makes sense. H2O has 3 atoms, so it's 0.03. NH3, ammonia, is going to be a little bit more. It has an additional hydrogen, so it's going to be a little bit larger. And look, this number is a little bit larger. Methane, again, a little bit larger. So we have that there. The larger the molecule, the more of a change you're going to have to make with the volume. So that's that. That's really all I have to say about deviations from the ideal gas law. Remember, it's just going to be those two things. How does this change the volume under low volume, high pressure situations? Because you have to subtract the volume that the atoms are taking up in a real gas situation. And then also remember those intermolecular forces, because it's going to attract and drag down the particles slamming against the side of the wall, i.e. pressure. So that's that. I will see you guys later.